Okay, so today we start with triple integrals. Uh, Both the theory and practice of triple integrals is very similar to double integrals. So, and first variable integral of first no one variable functions uh, is quite different than integral of uh, two variable functions, but after two they are all similar. So uh, the theory and the practice of triple integrals is very similar to double integrals. Okay, both the theory and practice of triple integrals is very similar to those of double integrals. So nothing is different basically. This time we will have a domain. So let D be a domain in R3. So it can be bounded domain or unbounded domain, something like this. Let's say a three-dimensional object. It can be something like this, a solid torus or something like a sphere, a three-dimensional object. By in the Cartesian coordinates, we had x, y, z, and we have a volume element, namely this kind of stuff. Something like this. Okay, so this is dx, this is dz, and this is dy. Okay, and dv is the dx, dy, dz, called the volume element. Okay, product of these three increments in x, y, z directions. The product of these is called the volume element. And so this is triple integrals. And for example, if we have a domain, let's say D like this, suppose it is a bounded domain. If D is bounded, closed and bounded with reasonable boundary. Reasonable boundary means something like this. It is not. It is not. So I mean, how to say? Something like this on the boundary. We will consider usually objects where the boundary are surface pieces or planes and so on. So they will be good enough for our purposes. But in general, the boundary of a solid region could be very, ugly, and you may not take integral actually. Uh, However, we will not consider those. So if it is, a reasonable surface or domain with reasonable boundary, then the volume of D is nothing but the uh, integral of this dv over the surface. What we mean by that, again, uh, this is defined again using partitions. So what we do, we divide the coordinate axis into pieces. Okay, let's say from x0, x1, let's say up to xn, and then y0, y1 up to ym, and then we have, let's say, z0, z1, and zk. Okay, and so you just draw parallel lines. Okay, like this. So you obtain some uh, grids like this. Let's say, okay, and you have also same thing in the z direction, and you just have this, all over. Okay, so in you just divide the tree space into little boxes. Okay, little boxes, and then so a typical box will be something like this. Okay, a typical box will be something like this. Let's say this is xi. Xi, no, xi is here. Xi plus 1, xi. So in the x direction, xi plus 1. In the y direction, let's say yj plus 1. And in the z direction, zk, zk plus 1. Okay. You compute the volume of this. Let me write it like this: I, j, and k, which is the product of xi plus 1 minus xi, yj plus 1 minus yj, and zk plus 1 minus z. Buna belki k dememem lazım. L diyeyim. Çünkü k'yı şey için kullandım. Okay, let me say L plus 1. ZL. And then we just, take these objects and sum over I, J, K, L. I from 1 up to, maybe I can write it this way, 1 up to N, J from 1 up to M, and L from 1 up to K. You add all these. This is an approximation for the solid object. Here, of course, we have some, solid object. let's say in the tree space, something like this. Okay. So when you divide the tree space into pieces, you divide this solid object D into pieces. You compute this sum whenever this. So you take you take Vij's Vijl into summation if this object with D intersects. Yani uzayı küçük küplere böldüm. Benim solid objemle bazıları kesişiyor, bazıları kesişmiyor. Hangileri kesişiyorsa onları alıyorum. Onların toplamına bakıyoruz. Tamam mı? O zaman bu bir şey olacak. Then the sum. Okay. Then the sum is an approximation for the volume of D. İki boyutta bu biraz daha kolay anlaşılıyor. Yani iki boyutta diyelim ki sizin bölgeniz şöyle. Ben bunu şeylere bölüyorum. Böyle küçük karelere bölüyorum. Bu karelerden D ile kesişenlerin hacimlerini alanlarını hesaplıyorum. D ile kesişenlerin. Bu tabii ki D'nin alanına tamamen eşit değil. Çünkü hani biraz daha fazlası var, değil mi? Şöyle. Bunları topluyorum. İçeridekiler de var tabii. Yani D'yi birazcık geçiyor bu. This is a little bit bigger than D. But you keep doing this with smaller and smaller, or finer partitions. Okay. We define norm of the partition P as P dediğim şey şu işte. Yazdım mı onu? Yazmamışım. P dediğimiz şey şu. Partition'ımız işte x0 x1 xn, bu diyelim ki A'dan B'ye kadar, sonra y0 y1 ym C'den D'ye kadar ve z0 z1 zk E'den F'ye kadar. Bunun normuyla, by the norm of this we mean the following. Maximum of over all ijk's, ijl, let's say, the following object, xi plus 1 minus xi squared, yj plus 1 minus yj squared, zl plus 1 minus zl squared, and then square root. So this is nothing but the diagonal of this object, right? The diagonal of this. So length of this diagonal. Okay. You take the maximum of this. You call this norm of P. Now, if you keep computing this summation over all partitions, so this is a summation over a partition P, right? Okay, so delta V, and you okay, şöyle yazayım, pardon. So I, J, L is in P olmak üzere ya da X, I, Y, J, Z, L P'de olmak üzere you form this summation which is just I, J, L X, Y, J plus 1, Y, J, L plus 1, Z, L. You form this summation, and if this sum has limit as norm of P goes to 0. So what we mean is this. We just keep dividing this region into smaller and smaller pieces. Okay. Smaller and smaller pieces. And I form the sum each time. This sum. If this number summations approaches to a number as the norm of the partition goes to 0, then we say that the triple integral exists. So if then we say that the triple integral dv over d exists and equals to the limit. O limit değeri neyse ona eşittir. Peki bu bir yerde birin integrali. Birin integrali. Başka bir fonksiyon alırsak if f x y z is a function on d, then we may form Riemann sums as follows. Yani bu bir tane partition aldığımız zaman işte yani x'ler, y'ler ve z'ler olsun. Tamam mı? Ve xi star seçelim. Bu nerede? Xi ile xi plus 1'ın arasında. Yj star seçelim. yj plus 1 ve zl star seçelim. zl plus 1. So in this actually a little box, okay, this was yi plus 1. This was yj xi plus 1, and this is zi not zl l plus 1. So what is this point? Xi star yj star ZL star, it's a point inside this box. Okay, somewhere here. So this point P, well, not P, let's say whatever, Q. Q is this point. Xi star, Yj star, ZL star. And what is the Riemann sum? Riemann sum is this. Okay, Riemann sum is this. You take summation over all ij else, and then you compute your function at this point and multiply this by the volume element I, J, L, and you take the sum. This is a Riemann sum, and if this summation converges, if the okay, let's call it this is a Riemann sum for the partition for the function f and partition p. If the Riemann sum converges to a real number as the norm of partition goes to 0, then we say that f is Riemann integrable over D, over the domain D, and we write the following: the integral, triple integral of f dv is equal to this limit of Riemann sums as p goes to 0. Okay. Tabi bu summation'da şey de var. Hani bu norm p'yi sıfıra götürüyorum. Yani bu her seferinde daha küçük küpler alıyorum. İçeride seçtiğim Q noktası Qij isterseniz diyelim IJL rastgele seçilecek IJL. Hangi noktayı seçersem seçeyim bu limitin aynı sayı olması lazım. Eğer öyleyse o zaman buna Riemann integrable diyoruz. Peki. Bu tabi eğer mesela f pozitif bir fonksiyonsa remark diyeyim. Remark if f x, y, z is positive on D, then we may consider f as the density of the object at the point x, y, z, and thus the integral above becomes the mass of the solid object D. Değil mi? Yani bu toplamda eğer bunlar şeyse, density ise siz ne yapıyorsunuz? So the density of the object at this point is this much. You multiply with the volume, you find the mass of this little cube. And then you add these little cubes, the mass of this little cube, so you get an approximation for the mass of the object. And then you just keep repeating this with finer partitions. In other words, you divide it into even smaller pieces and so on, so that you minimize your error in the computation. And if limit exists as p goes to 0, then the number you obtain is nothing but the mass of the object. Okay. So triple integral, if this function is 1, then it is the volume. If it is not 1, if it's a positive number, then it is the mass. What if it is negative? Well, then you may think it as anti-mass, right? Positive mass, negative mass. So still it's a mass. But some part may have negative mass. Or you may, consider other quantities. For example, F could be the amount of heat at that point, and when you sum that up, you get the total heat of the object. Yani toplam ısı miktarını bulursunuz. Doğru mu söyledim bilmiyorum ama yani sıcaklığı değil de. Okay, so you may consider different interpretations of this integral depending on what your function represents. Okay, and how do you compute these integrals? Again, uh, so as in the case of double integrals, we compute triple integrals by writing them as iterated integrals. Double integrali hesaplarken de öyle yapıyoruz. Mesela bir örnek yapalım. Şöyle. Example. Let B be the rectangular box given like this. X coordinate ranges between 0 and A. Y coordinate ranges between 0 and B. And Z coordinate ranges between 0 and C. We are asked to evaluate the following integral. I triple integral over this ball B of x y squared plus z cubed dv. So if this function, for example, represents the density of the solid object B at the point x, y, z, then this will be the mass, right? You are integrating density over the object, you obtain the mass. Okay, so this is, let's say, XYZ plane. So this is from 0 to A. So we have something like this. All right. Now B is this rectangle. Therefore, I can just write it like this. XY squared plus Z cubed. Let's first integrate with respect to X and then Y and then Z. So X coordinate ranges from 0 to A, 0 to B, 0 to C, and this will be what? So I first integrate this with respect to X, 0 to C, and 0 to B. integral of this with respect to x is just x squared over 2 y squared plus xz cubed, right? And x ranges from 0 up to a, and then I have dy and dz, 0 to c, 0 to b. When I plug a for x, I get a squared y squared over 2 plus a z cubed. And then I plug 0 for x. When I plug 0 for x, I just get 0, dy dz. And then we do what? We integrate with respect to y. All right. If I integrate with respect to y, I get a squared y cubed over 6 plus a z cubed y. And y is ranging from 0 up to b. And then I have dz. Okay, let's see what we get. When I plug b for y, I get a squared b cubed over 6 plus a z cubed b minus when I plug 0 for y, I just get 0 dz. And then we have what? Now I integrate with respect to z. So I get a squared b cubed over 6z plus ab z to the power 4 over 4. And then we plug c and 0. When I plug c, I get a squared b cubed c over 6 plus ab c to the power 4 divided by 4 minus 0. So this is what we get. The book uses also the following notation. So another notation for iterated integrals. As in the case of double integrals, there are two notations. One of them is actually preferred by physicists. I don't like this notation, but you know, this is something used. So here it is. The same integral can be written like this. Integral with respect to z, and then integral with respect to y, and then integral with respect to x. What was the object? X y squared plus z cubed, right? Dx. So they don't write like this, but they write it like this. It means first you integrate with respect to x. Whatever you get, you put it here and integrate with respect to y, and then you get something, and then you put here and you integrate with respect to z. They are the same thing, just different notations. Okay. Let's do another example. Compute this integral, triple integral, over a region T dv, where T is the tetrahedron in R3 with corners 0, 0, 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1. So it has 4 corners, 4 edges, and 4 sides. What is this tetrahedron? Okay, let me just draw. It has these corners. Okay, so it has 4 corners, 4 edges, and 4 faces. Okay, these are all one. Okay, I would like to compute this integral uh, over this region. All right. Now we just need to write this as an iterated integral. Well, how can we do this? Uh, Here, the coordinates doesn't have any actually advantage with respect to each other. They are, kind of uh, equal. So I can just start in any order. Let's do it as follows. Şöyle diyeyim. Suppose it was a double integral like this. Okay. 1, 1 in the xy plane. And T is the triangle here. How would you write this? Well, you could write it this way. Suppose this is x. X is ranging from 0 up to 1. And for each x, y coordinates ranges from 0 up to this point. What is this point? Well, this is the line x plus y equals 1. Therefore, for x here, y is just 1 minus x. So I would just write, okay, x is changing from 0 to 1, and for each x value, my region contains points whose y coordinate ranges from 0 up to 1 minus x. And that would be my iterated integral. What I will do here, I'll just repeat the same thing, but this time I have 3 variables. So what can I do for any, let's say, x here? Uh, so y coordinate ranges from this point to this point. What is this point? Well, this is x plus y equals 1 line. Therefore, this point has coordinates x and 1 minus x. So, for each x, fixed x, y ranges from 0 up to this point, 1 minus x. So, I write it this way. Pardon. X is ranging from 0 to 1, dx. And for each x, y is ranging from 1 up to 0 up to 1 minus x. And for each x and y, suppose you have this point. So this point has coordinates x and y. Uh, what about the z coordinate? Z coordinate in this domain ranges from 0 up to this point. What is this point? Well, it is on this plane. So I just need to write down the equation of this plane. What is the equation of this plane? Well, this is the plane that crosses the axis at 1, right? Each of them at 1. So the equation for this plane is this: x plus y plus z plus x plus y plus z equals 1, right? It is this plane. Therefore, z is just 1 minus x minus y. Therefore, my z values in this region ranges from 0 up to 1 minus x minus y. And then we integrate y. Of course, here I have dz. Tamam mı? Şöyle düzlem denklemini şöyle buldum. Bu yapmıştım onu da bir ara. Eğer düzlem eksenleri A, B, C'de kesiyorsa bu düzlemin denklemi. So if you have a plane that intersects the axis at A, B, C respectively, then the equation for the plane is this. X uh, over A plus Y over B plus Z over C equals 1. Değil mi? Bakın iki tanesini sıfır alırsanız, bunları sıfır alırsanız x eşittir a. Bu ikisini sıfır alırsanız z eşittir c. Bu ikisini sıfır alırsanız y eşittir b. Tamam mı? So this is a quick way of writing the equation of a plane. Once you know the intercepts of this plane with the coordinate axis. All right. Now you just compute this iterated integral. First, you compute integral of y with respect to z. Well, what is that? Of course, I consider y as a constant with respect to z. Therefore, the integral of y is just z times or y times z. And here z changes from 0 up to 1 minus x minus y. Okay. And then I have dy and dx. 0 to 1, 0 to 1 minus x. So for z, I plug this value and then this value. So let's do that. So this is y times 1 minus x minus y minus y times 0. All right. And then dy dx. So let me call this integral I. So we have what? I is equal to 0 to 1, 0 to 1 minus x. What is this? This is just y minus y times x minus y squared, and then dy and dx. Now I integrate with respect to y. So integral of y is just y squared over 2. This is just y squared times x over 2 minus y cubed over 3. And here I will plug 0 and 1 minus x for y. And then we have dx. Okay. When I plug 1 minus x, we get 1 minus x squared over 2 minus x times 1 minus x squared over 2 minus 1 minus x cubed over 3 and then dx. When I plug 0 for y, I get of course 0, so I don't write it down. This is what I get. Şimdi bir de x'e göre integrali alacağım. Okay. Şunun integrali kolay, değil mi? Bunun integrali, what is the integral of this one? It is 1 minus x cubed over 6. with a minus sign. Değil mi? Çünkü bunu türevini alırsanız 3 aşağıya gelecek. İçinin türevinden eksi 1 gelecek. Dolayısıyla bu eksi gidecek. 3'e böldünüz 2 kalacak. Üstü de 1 azalttınız. Hangileri? Ha, tamam. Güzel, tamam. Şöyle diyorsunuz değil mi? Bu 1 eksi x parantezine aldığım 1 eksi x'in kübü olacak. Bölü 2. Burada da 3 var. Dolayısıyla 1 eksi x'in kübü bölü 6. Right? Dx. And what is the integral of this? 1 minus x to the 4 minus over minus sign 24. Right? 0 and 1. Kontrol edeyim. When you take derivative, 4 comes down, you get 6. Minus 1 comes out, so this minus sign cancels, and you have cube here. So we have done correctly. When you plug 1, you get 0. Minus, when you plug 0, you get 1 over 24, but with a minus sign. So the answer is 1 over 24. Yes, correct. Okay. Okay, now let's have a break. After the break, let me continue.